Hello, welcome to the 3.2 Stormwater Science video. We're going to pick it up exactly where we left it, so there's not going to be recapping here. And we're going to continue with just the scenario based on our imaginary watershed model after the storm event. And we're going to continue to see how the conditions of the river change after a storm event. We are going to learn a little bit more about the impacts of that storm event and how we can do something in the future to change that or to help in any way. So let's get to it. So now that we have talked about flash floodings and about storm events and monsoons, and we have had our storm event happen in our watershed model, we can finally focus on the scenario after a storm event, which is the one to my right. So we're going to go back to our watershed model, and we are going to talk about these different cards that we already talked about during our recap, and we're going to see how each of those cards play a role in the after storm event model and how they change. So we're going to start with turbidity, and as we said, the turbidity is the amount of suspended solids that is in a sample, or the number of suspended particles in water. Some facts that you might not know about turbidity is that rivers constantly pick up dirt from the bottom and the sides. So there's always going to be some sort of turbidity. That's normal. And also that faster moving waters have higher turbidity than slow moving waters. That makes sense, right? When it goes faster in the water, it picks up more of these suspended particles or this dirt, making the turbidity go up. Now, after a storm event, we know that sediment is the largest non-point source pollution on Earth. And in case you don't remember, the difference between point source and non-point source is that type of pollution that you cannot point at it. So you don't know where it's coming from. And that makes sense because it comes from any place that has basically sandy particles that can end up in the river. Now, having too much turbidity can be problematic because suspended particles can get stuck in the fish gills, causing them to eventually suffocate. It can also make it harder because of vision for some organisms that live in the water to be able to find their food sources. So in general, if you had to predict what would be the turbidity after a storm event, would you predict that it would go up, down, or stay the same? And again, we're talking about the scenario after a storm event. Then we're going to talk about dissolved oxygen. Dissolved oxygen is the amount of oxygen that is dissolved in the water. Now, oxygen levels are directly depending on the temperature of the water. So if we have warmer waters, we know that we're going to have less oxygen than in colder waters where there's more oxygen. So summertime, you probably will have less dissolved oxygen than in wintertime. Now, after storm events, oxygen levels go up because when the raindrop touches the surface of the water, basically clears this splash that allows some oxygens to naturally get into the water and dissolve into the water. But also, oxygen levels can go down if there is too many nutrients that get washed into the river. And we will show you in a second why is that. So this is the diagram of a little bit what happens related to dissolved oxygen. So when it rains, there is a certain amount of nutrients that come from different sources that end up in the water. And what happens is when we get a lot of nutrients, we get an increase of algae. And when this algae dies, or there is a lot of died organic matter, basically there is a lot of bacteria that try to break down this organic matter, and these bacteria are using the oxygen. So eventually, because they are using all this oxygen, they drop the oxygen levels down and then can create fish die-offs, so that the fish die. That's a little bit the summary of this diagram. Now, I'm going to ask you the same. Think about the prediction for what would happen to the dissolved oxygen after a storm event. Would it go down, stay the same, or go up based on what we have talked about? The next is going to be the macroinvertebrates. And remember, macro means big, and invertebrates means those organisms that don't have a backbone. And these are also used as bioindicators because they tell you about the health of the water. They tell you about how clean or dirty the water is. And here it says that mayflies and stoneflies only live in clean water versus black flies and dragonflies that live in semi-polluted water. So these are some type of macroinvertebrates that can tell you, without doing any testing, how is the quality of the water that you are looking at. Now, If after storm event, if there is a lot more midges and aquatic worms, and you know that you're looking at a heavy polluted water. So it's important to look at these changes. If you're curious to know more about macroinvertebrates and related to water quality, I invite you to go to our website and look for the Stormwater Science folder, where there's a bunch of activities related to stormwater, and we have one that talks about macroinvertebrates, and it's a really fun activity. So I would definitely encourage you to try it. The next one is fish. Fish represent the different biodiversity of different species that we find in the water. There are more than 23 different species of fish that are found in the Rio Grande, but we know that an increase in pollution reduces the type of fish populations. Only 1/3 of the native fish that are known to have inhabited the Rio Grande are still found today. So that is something to think about when we're talking about all these different parameters. The next one is E. coli. And again, we said that E. coli is the bacteria found in the intestines of warm-blooded animals. And what we know is that E. coli is naturally found in all river ecosystems, and duck poop makes up to 22% of this E. coli in our river. When rain washes animal waste into the river, that can raise significantly the amount of E. coli. And particularly in cities like Albuquerque, where we have about more than 80,000 registered dogs that produce 20 tons of poop a day. So imagine, how much is that? So if we want to do a size comparison, we can look at this diagram. So 20 tons is equal to about the weight of 5 hypos, or the size of a bus, like this one in here. Now we're talking that these are 20 tons of dog poop per day, when if we consider having a total of 80,000 dogs. That is a lot. We need to be thinking about that one, especially if you have pets at home, like easy ways to reduce the amount of E. coli that ends up in the river from this source. Here we have a pie chart that shows the sources of E. coli in the middle of Rio Grande. And we can see that the biggest source of E. coli is this purple color, which represents the avian. So that means any type of bird. This is because we know that the Rio Grande is a place where there is a lot of birds that migrate and they use as a stop place during their migration. And it would make sense that there is a high amount of bird poop that ends up in the river because of that, because of the migration. But the second biggest source is the one that you can see here in yellow, which is canine. Canine is another way to say dog. So even though we can't control the number one source of E. coli in the Rio Grande, which is the one coming from birds, because we can't really control when birds poop and what we do with that, we can definitely control the amount of canine or dog poop that ends up in the river. And the third one, interestingly, is human or sewage. So that means that we are the third focus of E. coli in the river. The rest are things like wild animals, like raccoon and deer and coyote. And then we have other things like rodents. We include here our lovely porcupine and cows or horses. So based on what I just talked to you about and using the pie chart, do you remember what are the 3 main sources of E. coli in the middle of the Rio Grande? Next is nutrients. And nutrients are made of inorganic chemicals, mainly nitrates and phosphates. And they are usually used to grow crops. We know that the use of phosphate fertilizers have increased in the last 4 years from 9 million tons per year to 40 million tons per year. It's something that we should keep in mind. The use of synthetic nitrogen fertilizers has increased almost 20-fold to the current rate of 100 million tons per nitrogen year. That means that we're using a lot of phosphate fertilizers and nitrogen fertilizers, and usually they are chemically made. That means that they are hard to decompose. After storm events, an excess of nutrients can cause algae blooms that can block the sunlight from entering into the water, but also, more than that, algae dies, all this organic material is being decomposed by bacteria, and to do so, they need oxygen available. So that means that all these bacteria are using this dissolved oxygen available in the water to decompose this organic material, and that will plump the dissolved oxygen. So There's always connections between these two different components. So in this case, the amount of nutrients in the water is directly linked to the dissolved oxygen levels. And we know the dissolved oxygen levels, as we said, is also directly related to the temperature of the water. So there is always connection between one and the other. The next one is pesticides, herbicides, and fungicides. And just as a reference, the US agricultural industry uses about 800 million pounds of pesticides annually. Pesticides are not selective. It's not that they just kill this type of insect that you might want to kill. It kills everything, and that is problematic. Of the 30 more common used lawn pesticides, 16 are toxic to birds, 24 are toxic to fish and aquatic organisms, and 11 are deadly to bees. And just to help you with this comparison of the 800 million pounds, we used a comparison before, but the United States Capitol dome is 9.1 million pounds, and the Great Pyramid of Khufu is around 12 billion pounds. So we're talking an amount annually that is between the Great Pyramid of Khufu and the United States Capitol dome. Annually, every year, we dump all this amount of pesticides and herbicides and fungicides to our fields, which as a result might be killing a bunch of biodiversity. So we need to be more cautious of this impact. Then we have trash. 38,000 miles of ribbon are thrown away each year, enough to tie a bow around the earth. Every 3 seconds, a baby is born, and in that time, 140 cans are born. So just to get you a sense of comparison of the amount of trash that we generate year after year. After a storm event, trash falls into the Rio Grande and has the potential to end up on the shores of Australia because all oceans are connected and everything is connected. We are connected to the entire world's ocean through our Rio Grande, so it's something that we should be keeping in mind. Then we have oil and gasoline. And just to give you some more facts, Americans use nearly 400 million gallons of gasoline every day. Now, this is not only used in cars, it can be used also in big machinery, but that is a big amount of gasoline. Just to give you a size comparison again, an Olympic-sized swimming pool, which is the big one, can fit 660,000 gallons of water. Now, you would need 600 Olympic-sized swimming pools to reach the 400 million gallons of gasoline that are spent per day in the US. So if you had an aerial view of the 600 swimming pools, it would look something like this. Now remember that each Olympic-sized swimming pool is a huge swimming pool. So a huge amount of gasoil is being spent per day in the US alone. So if we have all this gasoline that is being used every day and that sometimes leaks, and then people wash their car in their driveway, all this oil and soaps ends up going down the storm drains. And because this water, as you remember from the beginning, it's not filtered, ends up directly into our river. If you properly dispose any oil and gasoline or any petroleum products at a local auto shop, we can help to keep our Rio Grande clean. Then we have medicine and other chemicals. How does the medicine end up into the river, you might wonder? Well, the first reason is by just pure consumption. Your body sometimes can't absorb all the medicine you are giving it to, and then you basically pee out the rest. So that goes down the sewer and eventually makes it into our Rio Grande. Another important point is that the necessary consumption of antibiotics, which is a very specific type of medicine, can create antibiotic-resistant bacteria. After storm events, animals end up drinking the medicated water in the Rio Grande as well. Remember, all this medicine flushes down the toilet, ends up into the river. And even though it goes through the wastewater treatment plant, sometimes it's really hard to filtrate out all these compounds from the water. Here is a graph of compounds that are found in the Rio Grande. We have this bar graph in blue, represent the type of compounds that are found upstream of Albuquerque. And in red, we have the ones that represent downstream of Albuquerque. And this is in the South Wastewater Reclamation Plant. This graph was made based on the analysis that was done in February 2018, so not that long ago. And we have two different types of graphs. The main one is here, but also we have a separate one. And the reason for that is because the quantity of these different compounds is so much bigger than the rest of them that we couldn't fit it in this scale. The graph will go all the way up.
So we had to create a separate graph for these particular compounds, and we will talk about those in a second. So in general, in this graph, we have in the x-axis the different compounds, and we'll talk about a few of those in just a second. And in the y-axis, we have the quantity of each of these compounds. So if we focus on medicine, which was the last card that we were talking about just a minute ago, we can see that amoxicillin, which is a type of antibiotic, can be found downstream of our cookie in fairly high quantities. We are talking quantities of a little bit less than 10,000 grams per liter. There is also other antibiotics that can also be found in less quantities. How does all this medicine get into the river in the first place? So as we said, there's two main reasons why they end up in the river. The first one is because people throw expired medicine and flush it down the toilet. The other reason is because you might end up taking a higher amount of medicine that you actually need. That means that your body can take it all in, and the rest of medicine that your body can't really use, you just pee it out and ends up directly into a river because it's really hard to filtrate even for the wastewater treatment plant. Then there is other compounds that might not be medicine. For example, sucralose is an artificial sweetener. We can find it here with quantities that almost reach between 50,000 and 60,000 grams per liter. But what is artificial sweetener? Does anybody know? These are some examples of artificial sweetener. Equal, Splenda, Sweeten Low, and also artificial sweetener can be found in a lot of diet products. For example, Diet Coke. It will also have sucralose. The way it works is when you take it, you taste the sweet in it, but because it's human-made, your body doesn't know how to break it down. So the same way that you drink it in, you pee it out. Your body can absorb it, which is one of the reasons why it's considered Diet Coke, because your body can metabolize it. But that means that all these artificial sweetener that you take it in, you pee it out, and it ends up in the river accumulating, which is a big problem. How can you help reduce the amount of compounds like some of the ones we talked just a minute ago downstream of a cookie? Can you think of some ways that you could help reduce the amount of compounds?
Okay, so we're going to leave it here for today. Feel free to click in the video Stormwater Science 3.3 if you want to finish up this lesson. We're going to be talking about the scenario after the storm event. We have just been talking about the parameters. And we also will be talking a little bit about how to understand all this data together. So we're going to do some graphing to try to understand how the river and all the communities are being impacted by the changes before and after a storm event. So if you're ready for the next step, let's move on to the next video. If not, see you next time. Bye.